Sorry. So it's my great pleasure to introduce Chris Oates and Takuo Matsubara, who are going to talk about a covariance function approach to prior specification for Bayesian neural networks. Takuo is a PhD student with Chris, and Chris is currently a professor at Newcastle University. You might have read quite a few of his papers because Chris has made quite a few interesting contributions to Bayesian statistics and Bayesian machine learning, especially stuff related to Gaussian processes. One line of research which is particularly interesting, I find, is this line of probability numerics, where you use probabilistic numerics, sorry, where you use probability and Bayesian statistics basically to assess the error in any numerical method. So this is a very astute and elegant approach because these methods are essentially deterministic, but it's so hard to come up with a good estimate of the error, and you use Bayesian inference to assess this error. And quite a few of interesting stuff relating to time discrepancies and stuff like that. And now I realize Chris is also working on neural networks. So quite a few interesting topics in his research interest. Before I let Chris and Takuo speak, don't forget that we have other talks in November and December from the various talks by Pierre Latouche and Sarah Filippi. And sorry for the auto-promotion, but I will also give a talk in a few weeks' time. To check the exact time and details, abstracts, so on, please go to the website of Laplace Demon Seminar. Right, yeah, people are already firing questions. Yes, that's very nice. Could we wait for the speakers to start their talk, if it's okay with you? All right, so Chris, I give you the floor.
Thank you very much, Nicola and David, for the invitation to speak today. So, the plan is for me to give the first half of the talk and Takuo to take over for the second half. Takuo is really, though, the leader of this project. So Takuo joined me as a PhD student about 1 year ago, and it's been really prodigious. And he's come up with a very exciting new approach to prior specification for Bayesian neural networks that we're going to talk about today. But I wanted to make a disclaimer, actually, that the Bayesian neural networks are something that are quite new to me as well. So I learned a lot during this project, and my practical experience with them is fairly limited. So what we're hoping for today from you guys is actually to get some real meaningful feedback on whether you think these ideas might be useful or not. You are likely to have more experience with these than we do, and we'd be really grateful either during or after the talk for your comments. Okay, so this is actually joint work with three people. The third person is Francois-Xavier Briand, who is a lecturer in statistics at UCL in London. And the outline of the talk is as follows. So I'm going to introduce very briefly Bayesian neural networks. I'm not even going to mention Gaussian processes. I'm going to assume a little bit of familiarity with Gaussian processes. I hope that will be okay. Then I'll explain what our contribution is, which is about prior specification for these things, which we'll see called Bayesian neural networks. And then we'll swap over, and Takuo will show some prototypical examples of these Bayesian neural networks in action, and then explain a little bit about why we can expect the method we're proposing to work from a theoretical perspective. Okay, so Bayesian neural networks, I'd just like to quickly point out, are not a new idea at all. The literature on neural networks goes back even further than Bayesian neural networks, but Bayesian neural networks have been traced back at least to the late 80s. Here's a couple of examples. I don't know if these are the earliest references, but they clearly make the point that these things are, what are they, 3 years old now, so they've been around. And they've not seen a huge amount of practical attention. And I think in a large part that is because of the difficulty of prior specification, which is what I'm going to talk about shortly. But what I'd first like to explain is why uncertainty quantification is important. And I think this will be clear to many people, but it helps to just to cement the idea at the start of the talk. So let's think about a typical machine learning problem like regression or classification. So you have a machine learning method which makes a prediction about the value of let's say a scalar response given some inputs, or perhaps it predicts a label, a class label, given some covariate information. And uncertainty quantification refers to the idea that you express the certainty or uncertainty in that prediction. So here's a picture. So if you've got a classifier that is attempting to assign names to objects in pictures, then you would assign the name of the object which you think is most likely. So in this case, the classifier says this is a sheep. Fine. It says this is a person. Well, no, but okay. So this is a cat. No, that's wrong. What this sort of straw man classifier on the left doesn't have is uncertainty quantification. So it could actually be the case that the balance of probabilities is more or less uniformly distributed between all possible classes. And if you have that uncertainty quantification, you can make use of that. So here in the middle is an example where uncertainty quantification is helpful. So here it says, this might be a person, but I'm not sure. There were many options that were equally plausible, and the person just happened to be slightly more likely. And that's useful information. So if you had uncertainty quantification as part of your predictive output, you can use that. So perhaps if you had high uncertainty associated with a prediction, you could just choose not to make any prediction at all. And that's what this third column is representing. In this case, we're very confident this is a sheep, and we label that as a sheep. Here, we're not confident, here we're not confident, and we just don't make any prediction. And that's potentially a desirable behavior. This is the kind of behavior that you can get if you have uncertainty quantification, but it has to be meaningful. It has to make the amount of uncertainty you have needs to reflect something physically meaningful. Let me just give you one more high-level concept. So if you have uncertainty, you can start to unpick what kind of uncertainty you have. So this is I think, quite a well-known example where you're trying to develop algorithms for self-driving cars. And there are at least two types of uncertainty that you might encounter here. So here are three different scenes. These images are segmented by the algorithm. And then the heat maps you see in these two right columns represent different types of uncertainty regarding different parts of the image. And what you're seeing in this panel here is essentially uncertainty related to not having enough data entering the camera on the vehicle. So all the uncertainty is really in the foreground, in the distance. And this kind of uncertainty, you don't need to be worried about, because you're going to have time to drive closer to these objects in the, so I shouldn't say foreground, in the distance. You're going to have time to drive closer to these objects in the distance to gain more information. So this kind of uncertainty is not necessarily worrying. What is worrying is perhaps this kind of uncertainty, where you have a lot of data on an object and you can't classify it. So in this case, the algorithm is being thrown out by paving stones because they look like sort of independent objects, but really it's just the floor. So there's a lot of uncertainty here that is kind of saying, well, I don't know what this is, and this is concerning because it's very close to me, and I've got a lot of data and it's not helping. So once you've got the language of uncertainty, you can start to actually be a bit more nuanced about what kind of uncertainty you have and whether or not it's something that you should be concerned about. So that's just a high-level motivation for why uncertainty quantification is important. And what we're going to do in the talk is much more specific. So we're going to look at one class of regression or classification method and talk about how we can endow it with the ability to quantify uncertainty. So that class of method is going to be a neural network. And pictorially, neural networks look something like this. I'm not going to go into a huge amount of detail, but the arrows indicate dependence and the nodes indicate scalar quantities. So this scalar quantity depends on these two scalar quantities. They all get combined in some potentially complicated way, and abstractly, we have a mathematical relationship between x, which is the things that go into the network, and y, which is the value that comes out of the network. And viewed in this mathematical way, this is a regression model. And the aim in regression is to find a model, by which I mean a line, which goes near to or through data. So in this picture, the crosses represent data. The blue line represents a fitted regression model. And that's absolutely fine. You could fit a regression model by estimating an appropriate value for theta, which is a Greek letter I'm using to represent all of the unknown parameters that might be present in the neural network. The role of uncertainty quantification here is to say how certain we are about the value of theta on the basis of data that we have. And if we have uncertainty quantification, we can lift that into the physically meaningful output space of the network. So here, the shaded blue area represents how certain we might be about where the mean of the data is, or actually, I don't know where this picture's come from. This might also be a credible interval. I don't know the provenance of the picture, but clearly it represents the extent, in some sense, to which you are certain about where the data are going to lie. So we perform uncertainty quantification in lots of different ways, but the predominant way we perform it is in Bayesian inference. So in Bayesian inference, we quantify uncertainty using something called the posterior distribution, which is proportional to the product of the likelihood, the probability of observing the data set given a fixed value of the parameter, and a prior distribution on the parameters, which quantifies your a priori guess about which parameters are likely to be suitable for this problem. Okay, and armed with a posterior, we can predict future outputs with uncertainty attached to our predictions using this formula, which is just a consequence of the basic axioms of probability. So there's another class of regression models which I think many people will be familiar with, and actually I'm going to rather hope you are familiar with them because I don't have time to introduce them. But they're called Gaussian processes. And a Gaussian process is a very flexible approach to regression that acts on the premise that the values of y that you're going to see are jointly distributed according to a Gaussian. Okay, and that the mean and variance of that Gaussian should be determined just as a function of the inputs x. So that's, in a nutshell, a Gaussian process. And Gaussian processes are widely used, but they're used in applications where uncertainty quantification is first and foremost the goal. And I contrast that with neural networks, which are used in applications where having a good predictive accuracy in the sense of, for example, a cross-validation test error is the goal. So the panacea here is really to have the good predictive performance coupled with a meaningful notion of uncertainty quantification. And that's not something we claim to achieve in this work, but that's clearly the goal, is to combine the two strengths of these different regression methods. And I'm saying regression just because for the purposes of drawing pictures in this talk, I'm going to be using regression as an example, but the idea is clearly applied to classification and other modeling problems. So why don't Bayesian neural networks give meaningful uncertainty quantification? Well, I mean, they might be able to, but it's tricky to know how to choose the prior distribution. So if you recall from the Bayesian framework, the prior distribution strongly determines your posterior, and therefore the uncertainty quantification that accompanies your predictive output. And it's not at all obvious how to elicit a prior for the parameters of a neural network. So we're not going to say what the parameters are just yet, but essentially there's a finite list of scalar quantities that are involved in specifying a neural network. And the default thing to do is to endow these with a multivariate Gaussian prior, where each parameter, each scalar quantity in this vector of parameters, is considered to be independent. Now that doesn't work terribly well. And here's an example of where it can go wrong. So the x's are again training data. The blue curve is a posterior mean, and the shaded region is some measure of uncertainty. And what you see is that in this region here, where we don't have any data, there's very, very low uncertainty. And that seems inappropriate just from an intuitive perspective, that if you were provided with these crosses and asked to fit a regression model, you would probably be uncertain in the region where you didn't have data. It doesn't seem to affect the predictive performance here when it extrapolates, but in this region, this seems very unreasonable. And we can contrast this behavior to the behavior that you can get by running a very default Gaussian process regression model, which is shown on the right here. I hope you can see this. I've got the Zoom window in the way, but I hope you can see the full slide. So in the region where there are no data, the Gaussian process has uncertainty attached to the prediction, which increases, being maximal when you're furthest away from any of the data. And that is intuitively the kind of behavior that you'd want to see in a model for your uncertainty. So we are faced with this problem that the default priors for Bayesian neural networks don't seem to work, and we're asking, what can we do about that? Okay, this was just to further make the point that the prior is not very meaningful. So if we sample values for the parameters of the Bayesian neural network and then lift the output of the Bayesian neural network to the function space, which is to say we just plot the corresponding regression function, then we get samples that look like this. And we contrast these samples from the prior distribution of the Bayesian neural network to samples from the prior distribution of the Gaussian process. So these are clearly very different. The Bayesian neural network seems to extrapolate linearly in the tails and otherwise do sort of somewhat constant behavior in the center. Gaussian processes are sort of stationary in this particular case. It's clearly very different. So the question you could ask is, well, if Gaussian processes work well for quantifying uncertainty, can we get similar behavior with a Bayesian neural network? And how would we have to choose the prior distribution in order to make these samples from the prior distribution of the regression model, somewhat qualitatively similar to the GP samples? And that's how we're going to pose this question today. So this avenue of work has received attention from different directions in the past. And one very well-known result is that if you take a one-layer neural network, which is to say something like this, and you consider a limit where actually the width of the network, which is the number of nodes in this middle layer, goes to infinity, then you can actually show using a kind of law of large numbers argument that the limiting Bayesian neural network is actually a Gaussian process. Think central limit theorem, the average of Gaussian things ends up, sorry, the average of anything with a second moment ends up being Gaussian. That's kind of the phenomena here. And you can actually write down what the limiting covariance function would be. And it's such that the GP prior looks something like this. So it's not a terribly satisfactory prior distribution. So this is kind of interesting, but it doesn't provide a practical way of constructing priors for Bayesian neural networks, right? So it shows you that in some limit of a neural network, you get a prior distribution, which is not particularly good. But it provides some analytical insight. Two of the questions that we're going to answer are as follows. So we're going to want to know, okay, so if we take a Gaussian process and we aim to come up with a distribution for the parameters of a Bayesian neural network that approximates in some sense that Gaussian process, when can that even be possible? And we're going to answer that by saying it's possible actually quite generally. You'll see the details later, but essentially if you're allowed to take a big enough network, you can get an arbitrarily close approximation to the Gaussian process with error measured in a specific sense, of course, that we'll come on to. And that will be possible whenever the Gaussian process that you would like to approximate has a certain amount of smoothness. So essentially the mean and covariance function are differentiable, but again, details are for the second part of the talk. And we're going to attempt to construct an approximation to a Gaussian, which can be shown to be consistent. Okay, so in a nutshell, we are going to attempt to construct a distribution for the parameters of this Bayesian neural network, such that instead of having prior samples that look like this, we'll have prior samples that look like this. And these will be theoretically guaranteed to share essentially identical statistical properties to samples from a Gaussian process. And this may be useful because for the reasons that we talked about at the start of the talk, endowing Bayesian networks with uncertainty that's meaningful is an important problem. Here's a picture of what's going to happen later, but I'm going to leave that for Takuo to explain. So how do we do this then? So we've decided that Gaussian processes quantify uncertainty in a meaningful way, and that we'd like to construct a distribution for the parameters of a Bayesian neural network such that the output of the network approximates the Gaussian process. Well, there's an interesting idea that comes from the field of harmonic analysis that's going to underpin our construction, and it's called the ridgelet transform. Now, this is going to require a couple of slides to introduce, so we're going to pause and we're going to go on a sort of, say, mathematical tangent, and then we'll return and we'll see how we'll use this. But I'm going to introduce this concept of a ridgelet transform. So the ridgelet transform dates back to 1990s. It was developed by people including Emmanuel Candice in his PhD thesis, and it's an integral transform. So what that means is, for a sufficiently regular function f, I can represent f as the following double integral. So what I do is I take f and I integrate f, I sort of convolve f, if you like, with some other function psi to be specified. And that provides a sort of transformed version of f. And then I can recover f by applying a second integral against another function phi. So what does this look like in pictures? Oh, well, I guess I should mention. So, I mean, clearly, this equation is not going to hold in general, right? So I'm going to have to pick a very specific choice of phi and psi in order that this equation might hold. And it turns out that phi can be taken to be essentially almost any of the activation functions that you would see in a neural network. And that's going to be important later. So for example, phi could be the ReLU activation function, or perhaps something more sophisticated. And in order for this identity to hold for all sufficiently regular f, we'll need to choose the function psi in a very particular way that depends on phi. And for the ReLU choice, for example, the corresponding function psi should be this particular function, which happens to be the fourth derivative of a Gaussian. The specific relationship between phi and psi that needs to be satisfied is this one here. And it can be shown that if this equation holds, then this equation holds. And you can enumerate pairs of activation functions and functions psi for which this relationship holds. Okay, so intuitively, what we're doing is we're taking f and we're convolving it with psi, which is going to map f into some other function space where the arguments of the function are now w and b. Okay, so w is a vector, a d-dimensional vector, and b is a scalar. Okay, and these w's and b's, the notation is intentionally chosen to be suggestive of the weights and the biases in the neural network, and we'll make that connection later, but that's why w and b are here. So the first step is we take our function f and we transform it. So f lives in some nice space of sufficiently regular functions. Here's a picture of an f. And we transform f by convolving it with psi, leading to another function, which we can call tau. Tau now has two arguments, w and b. So tau is, in this picture, it's a two-dimensional function. And then the identity here says that this transform is invertible. So we can take tau and we can return 2f by convolving tau now with this function phi, which is analogous to an activation function in a neural network. Okay, so this is all harmonic analysis, and it's not clear yet what this has got to do with anything apart from, that I've called this an activation function. So let's see what the connection is. Oh, and just for those of you who find this useful, you can draw an analogy between the ridgelet transform and a Fourier transform. So if you're familiar with Fourier transforms, you take a function f, you map it into a frequency space, and you can return to f by applying the inverse Fourier transform. That's a loose analogy of what's going on with the ridgelet transform. Okay, so why is this useful? It's useful because if you discretize the ridgelet transform, something very interesting happens. So let's take these integrals here and replace them with cubiture rules. That is, for the inner integral, for example, you replace the integral by a sum over a finite set of values for x, and these will be weighted in some way such that the discretized approximation converges to the integral in a limit of using infinitely many values of x. So we'll do that with the inner integral, replace the integral over x by a sum over some values of x and some weights, and we'll do the same for the outer integral. So replace that which is an integral over W and B, by a sum over certain values of W and B, and again some weights. And okay, so this is now starting to look interesting, because what we've got is an approximation of f. Okay, so integration introduces an approximation. So what we've got on this line here is an approximation of f. And if we look at it, this is actually now a one-layer neural network. So phi is the activation function. This is some constant in x, and this is a constant. And we have a sum over the weights and the biases. So this is a one-layer neural network with n hidden nodes and activation function phi. And this is actually what the ridgelet transform was designed to express. So it's kind of like a continuous version of the neural network. And we can get a neural network that approximates f by taking f and applying a discrete version of a ridgelet transform. Okay, so this is very interesting. There are, of course, many choices for the cubature rule. But if you use Monte Carlo cubature, then this thing starts to really look like a Bayesian neural network. So in Monte Carlo cubature, your discrete cubature nodes for x and w and b are just samples from some probability distribution, independent, identically distributed. So if we let the wi's and the bi's, these cubature nodes, be independent random samples from some distribution, let's call it lambda, then this thing starts to look very much like a Bayesian neural network. So in a Bayesian neural network, you would sample values for weights and biases from the prior, and that would allow you to generate bias samples in the output space of the network. The only caveat here is that there's actually an additional set of parameters in the neural network, and they're called C. So once you've fixed your biases and your weights, you still need to come up with coefficients for these activation functions, and we'll call those coefficients C. And C, if you follow this argument about discretizing a ridgelet transform, these C's are deterministically related to F, and they depend on the WI's and the BI's, because you can see them faintly through this orange box if you look closely enough. So this construction is interesting, and it differs from the conventional approach to a Bayesian neural network, because it says that the coefficients here ought to encode some dependence on the biases and the weights. So this is kind of the idea that we're going to exploit. We're going to come up with a distribution for these coefficients given the weights, such that our implied Bayesian neural network has statistical properties that are closely related to a Gaussian process. And how do we do that? Well, let me just go back and show you the expression for each coefficient. And you can see that this expression for the ith coefficient depends linearly on the function f. So suppose that f was a stochastic process with the structure of a Gaussian process. And we would like to approximate that Gaussian process using a neural network. Well, I have a recipe for what the coefficients of the neural network would be for a given f. And if f was a sample from the Gaussian process, I can compute what the implied distribution over the coefficients would be. So it would be a Gaussian because of the linearity property. And it would have a mean, let's call it U, and a covariance matrix sigma that are derived from the mean and the variance of the Gaussian process I was trying to approximate. So if f in my sort of target Gaussian process has a mean function m and a covariance function k, then the induced distribution on the coefficients of the neural network would also be a Gaussian because of the linearity, with mean some matrix times m, and covariance some matrix times the covariance matrix of the Gaussian process times the transpose of some matrix. It's a linear transformation determined by the matrix psi of the original Gaussian process. So this is the core of the construction. If we can identify a Gaussian process, then we can place a distribution over the parameters of the neural network such that the corresponding Bayesian neural network has a distribution that is in some sense very close to the Gaussian process. And the sense in which it is close is going to be made clear in the second part of the talk. But this is the idea. So what do we need? We need to pick a Gaussian process that we're aiming to approximate. we need to work out the function psi, which partners with the activation function of our neural network in order to ensure the ridgelet transform identity holds. We need to pick a quadrature rule for the inner integral here, which is a quadrature over x, and we need to this is kind of a detail. I won't talk about that. Okay, and what does that transformation look like? Well, you can go through the derivation, but it's not particularly difficult. So we look at the expression for these coefficients here. We see these are a linear projection of f. What does a linear projection of f look like? It looks like what it should look like. Linear Gaussian calculations are relatively standard and not particularly informative. So I'm going to skip this slide. Okay, so that was a construction of a one-layer Bayesian neural network by application of the ridgelet transform to discretize a Gaussian process. What about deep neural networks? Because of course this really strong predictive performance of neural networks is typically realized in the context of deep networks. Now we don't have any mathematics to show you about deep networks today, but we do have a natural generalization of the construction of this prior. We're going to call this the ridgelet prior for obvious reasons. And the construction that we advocate for deep networks is kind of the obvious one. So conditional on lower layers, we specify the distribution of the next layer in exactly the same way that we've just seen for one layer. Sequential application of the ridgelet transform, which leads you to a reasonably straightforward description. Of course, there's some linear algebra here because we've got potentially large neural networks, so large numbers of activation functions. And we need to perform linear algebra to compute the covariance matrix of the coefficients of these activation functions. And there are actually, by this point, very standard approaches to making sure this linear algebra is stable and so on. So singular value decompositions, for example, when covariance matrices are close to singulars, this is the kind of idea that we can exploit to make this work in practice. Okay, so I think that was it for my first part of the talk. And this would probably be a good point to take any questions if there are any at this point before I hand over to Takuo. Oh, so okay, so there's one in the chat window. So, okay. Other than normal and ridgelet prior, did we try any other priors? No. So the literature on Bayesian neural networks is growing very rapidly, and an important task is now to benchmark the very many different proposals that are being put forward on standard test data sets. And what we hope to do is to develop this ridgelet prior to a point where it can be run in a stable and reproducible way in order to add our method to these comparisons. But it's still at the prototypical stage, so we haven't quite got there yet. That is the goal, though. Thank you. Right, well, thank you very much for your attention in this first half of the talk. Oh, sorry, Nicola, was there a further question?
Yeah, sorry. So I tried to speak, but I forgot to mute. Sorry for that. And before, at the beginning of your talk, there was Amir who was asking, is there any implementation of Bayesian neural networks using STAN?
Using STAN. There are examples using STAN. Now, that's not what we did in this project. And the reason for that was we're going to present results that are primarily for one layer neural networks. And one layer neural networks have a conditional Gaussian structure. So if you fix the W's and the B's, then the C's are conditionally Gaussian. So you can actually do something quite nice. You can marginalize over the C's to get a Gaussian marginal likelihood. And then the W's and the B's are relatively unconstrained by the data. So something like an elliptic slice sampler works really well. So we actually found a very simple MCFC method that worked for our applications. Going forward, we would need to look into computational methods for approximating the posterior distribution. And that could potentially be very hard.
And the other question Amir asked at the beginning is, and maybe it's related actually to what you have just said, could you also please highlight some of the open research problem with Bayesian neural networks? It's in the answered section if you want to look.
Sorry, I didn't quite catch which section that was, Nicola. Could you say that again?
So could you please also highlight some of the open research problem with Bayesian neural networks? Yeah, sorry.
Yes. Yeah, so the challenges are at least twofold. So I want to sort of emphasize that this isn't really my area. I'm quite new to the topic, but the challenges are absolutely in terms of prior specification. How do you ensure that you have interpretability in the output space of the network is an important research task because of the nonlinearity of the mapping from parameters to the output space. This is challenging. There have been some attempts to bridge that gap, and ours is one of these attempts. Other attempts involve using very specific activation functions or very specific architectures of the network, which allow you to encode something that you might know from physical considerations into the output space. So for example, monotonicity, periodicity, these kind of features you can encode in a neural network by carefully choosing prior or the architecture or so on. But to our knowledge, there aren't really generic methods such that you can come along with a covariance function and then you can work out what distribution on the neural network parameters would sort of match the features of that covariance function. There's a couple of sort of variational attempts to do this, but nothing with a consistency guarantee that we're aware of until this. The other problem is the one that we just talked about, which is the computational problem. So variation inference has been widely used to fit Bayesian neural networks with different degrees of success, and there's clearly some open challenges there. There's more fundamental challenges that impact on Bayesian neural networks from the neural network community. So I mean, it's not known whether the fitting procedure and the artifacts and idiosyncrasies of the stochastic optimizer actually have a role in the predictive performance. You know, could it be that finding a large shallow minimum is better than finding a global minimum for prediction? And these questions all have counterparts in Bayesian neural networks, which I think, you know, we're a very long way from understanding.
And in the meantime, we got two other questions. One from Alvaro. In your motivation, you mentioned that using GP regression is costly. Is the convergence and discretization process still less costly than Gaussian process regression, even for deep neural networks?
Yeah, thank you for the question. That's a good one. Yeah, it gives me an opportunity to explain a bit more the motivation. So if you can use a Gaussian process, then I think that's absolutely fine. We're interested in the regime where the highly sort of nonlinear nature of a neural network gives you some advantage over Gaussian processes. And then the question we want to ask is, can we make the uncertainty quantification a bit more meaningful? So our aim is not simply to perform similar calculations to a Gaussian process on the cheap. It's rather, can we set up the Bayesian neural network in such a way that it's got the chance to learn meaningful uncertainty, but still have the flexibility to be nonlinear where it has to be. And this is preempting a little bit the second part of the talk, but what we're going to show is that in some sense, the samples from the Bayesian neural network are close to samples from the GP in a sort of in an epsilon ball sense, but not in any other sense. So not in terms of number of derivatives or kind of higher order features. So our Bayesian neural network, although it's going to be close to a Gaussian process in a certain sense, it's got much more flexibility. It can be discontinuous, you know, all sorts of things can happen, and it's got the ability to learn that from data. So we're not advocating this is a computational replacement for Gaussian processes. We're saying if we can set the Bayesian neural network up, initialize it in a way that it's close to a Gaussian process, then this is going to give it a better chance to learn well and learn meaningful uncertainty.
One last question, and then you may want to go on. Any possible direction you see that Bayesian neural networks could help in interpretability of direct DNNs?
Interpretability of? DNNs,
I guess it's deep neural networks, I guess. Yes.
Okay, thank you. Yeah, I mean that is the very much the goal, I think. So we're not aiming to interpret the individual parameters of the network. All the interpretation is going to happen in the output domain of the network. So for all these regression examples, the output domain is the space where the regression happens. The other questions around interpretability that are interesting are ones like which of the samples led me to this conclusion, which of the training data led me to make this prediction for this particular test problem, or which of the inputs of the unlabeled data were driving the prediction of the label. And I imagine that uncertainty has an important role to play in that, but it's not something that we're directly addressing in this work. Yeah, but no, that's a very interesting question. I'd like to think about it a little bit more. Maybe I can think about it and say something at the end.
Yeah, maybe I would just like, I think when things like convolution neural networks might be an interesting thing to draw upon here as well, that there is some, maybe there isn't an obvious analog with a Gaussian process for something like a convolution neural network that at least that I know of. Anyway, that was like maybe an extension. I've got no idea if you've got any thoughts.
Thanks, David. No, I don't have any thoughts, but I think I agree with you that there's clearly a lot more flexibility in neural networks, and that must explain to some extent their success. The idea that you over-parameterize and then regularize is a hot one at the moment, and maybe that's the reason why these things work. But yeah, no, that's very interesting thing for us to think about. Cool. So thank you very much for those questions. I'm going to hand over now to Takuo, who's going to lead you through the second part of the presentation.
Maybe, Chris, do you mind maybe taking 2 more questions from the audience?
Oh, of course, yes.
Sorry. So Sarah Wade, who is actually going to give a talk in December in our webinars too. Let me take this opportunity to advertise her talk. Ask, in your motivation, you highlighted, in your motivation, you highlighted improved predictive powers of Bayesian network, the Bayesian neural networks over GPs. Are you referring to deep Bayesian neural networks? And what are your thoughts on deep Gaussian processes?
I'm not familiar with results that say that deep Bayesian neural networks are better than GPs, but certainly classical non-Bayesian neural networks have been shown to perform much better than kernel-based methods in some examples. Not all examples. There's some counterexamples in literature, but in many examples. And I was just inferring that that's probably going to be the case for Bayesian neural networks as well, because they're clearly based on classical networks. But the second question is that's a really interesting one. So deep Gaussian processes, to just calibrate my understanding. So the idea is that you fit a Gaussian process, but the covariance model for that Gaussian process is itself generated from the output of another Gaussian process, and this whole thing can be iterated many times over to provide a highly flexible parameterized regression model. And in that sense, it's very similar to a deep neural network. That's very interesting. So I don't have experience with them. The reason that we're picking neural networks as our starting point here, because we could have picked deep Gaussian processes, but the reason we're picking neural networks is that the ridgelet transform has already been developed, and we know how to discretize it. So we know how to go from the continuous transform to the Gaussian process, and that's going to be the hook that allows us to do theory. So if we can control the approximation error by discretizing the ridgelet transform, then we can actually say something about how close the neural network is to the thing it's approximating, and that's what we'll see next. I don't think that exists for deep Gaussian processes yet. So so I don't know how I would take a function and then sort of consistently approximate it in a way which was like the output of a deep kernel method. But if that could be done, then there's no reason you couldn't take exactly the same approach with deep Gaussian processes, and that could be very interesting. Thank you, Sarah.
And one last question from an anonymous attendee. Will it be completely non-Bayesian or biased to train a general neural network and use that as, say, means for distribution of priors?
So this is an idea that has been expressed by others, I think, that you would, it's sort of related to pre-training. You take a bunch of things which are not your data, but are but which contain sort of similar statistical properties to the properties you'd want to encode in a prior, and you pre-train a neural network on this kind of data, and you hope that the parameters of that neural network are then initialized in such a way that when you fit the neural network, and I'm thinking of just the classical neural networks here, you're more likely to hit a useful minimum that's physically meaningful. So that idea might extend in the Bayesian context. So you would take as your prior in the Bayesian neural network the posterior from a previous analysis where you'd fit two data that have a similar statistical character to what you'd like to encode in your prior. So that's very interesting, and I don't know if that works well or not. But the idea of pre-training has been around at least in the non-Bayesian setting. So yeah, that would be interesting to try. Yeah, thanks for making the suggestion.
Thank you. And now we are switching to our second speaker, Takuo.
Mm-hmm. Okay. Can you see my full screen?
Yes, I can.
Okay, thank you so much. So thank you for handing over, Chris, and thank you so much for Nicola and David for inviting Chris and me. As Chris mentioned, the ridgelet transform have been developed from 1990s, which have gotten many interest recent years because of the growing interest to wide variety of perspective of neural networks. And I had fortunately, I had some experience of studying ridgelet transform thanks to my previous supervisor who made an initial and early age contribution to ridgelet transform. And in the research discussion with Chris and FX, we came across with some thoughts that the combination of BNN and the ridgelet transform, which is new combination to Oates knowledge, could contribute to some open question in BNN. So that's how our endeavor to investigate on the prior specification of BNN began. Okay, so Chris explained this format 2 section. And okay, so from now on, I'm gonna talk about the remaining section, the experiment result of the ridgelet prior and the theoretical analysis of the approximation error. So we'd like to begin with the experiment results. So in the experiment section, we firstly show you that prior predictives of shallow Bayesian neural networks and the deep Bayesian neural networks. Okay, so in this slide, I'm showing the prior predictives of one hidden layer Bayesian neural networks. So we implemented one hidden layer Bayesian neural networks with the ridgelet prior, which had n hidden units as illustrated below. So the activation function of BNN is hyperbolic tangent here, and the target Gaussian process of the ridgelet transform, ridgelet prior, is given as this. So the mean function is 0, and the covariance function is given as the Gaussian covariance. Okay, so and as Chris explained in the former half of this presentation, we need to prepare these for other quantities. So in this experiment, we set this second derivative of the product of Gaussian function and a sine function as this function psi. And also the grid points over some interval from -5 to 5 is evaluation point xj. And for the first layer prior, we simply set the isotropic normal distribution, which have variance sigma w and the sigma b. And we set this specific value for the scaling constant mu I. Okay, so, and we also note that, we directly note that this scaling constant mu I depends on the variance of the first layer prior PW and PB here. Okay, and based on this setting, the right-hand side picture shows the sample pass behavior of target GP, and the left 3 picture shows the sample pass behavior of Bayesian neural networks, which have different number of hidden units n. So basically, we expect that the sample pass behavior of BNN get closer and closer to the original GP as the hidden unit number n increase. And actually, we can see that for larger n, the sample pass behavior looks sufficiently close to the original Gaussian process. So we can say that some property which Gaussian process have successfully induced to the Bayesian neural network sample pass space. Okay, so this is a result for the one hidden layer Bayesian neural network. So the actually same things happen even for the deep Bayesian neural network. So in this slide, I'm showing the prior predictives of 3 hidden layer Bayesian neural network. So the experiment setting is almost all same as the previous slide, and the ridgelet prior is applied for each layers, layer by layer. So in this picture, also we needed some relatively larger number of hidden units n compared to the previous shallow case. We can see that the Bayesian neural network sample pass looks sufficiently close to the original Gaussian process when we have large number of n. So, we would say this is a quite inspiring result, because we may know let's say, for example, when prior is set as just isotropic normal distribution, we tend to have the chaotic sample pass behavior or some constant like sample pass behavior. But in this case, we can see that Bayesian neural network have some sort of nice property such as smoothness or smoothness or something. So one of the significant difference between the vanilla prior, such as isotropic normal, and our ridgelet prior is correlation. So in case of the isotropic normal distribution, we don't have any correlation in each dimension parameter. But in the ridgelet prior case, we have some special structure of correlation between each dimension of parameters. So we would say this special structure of correlation could be sort of key or good ingredients to design nice sample pass property of Bayesian neural network. Okay, so we next consider the posterior predictive of one hidden layer Bayesian neural network. So for this experiment, we use the dataset called Mauna Loa CO2 dataset, which is well known for Gaussian process regression context. So this dataset represents monthly CO2 concentration of Mauna Loa volcano in Hawaii. So this means each input is time, and each output is the total amount of CO2. So we scaled this dataset to interval from -5 to 5, and we used the first 70% of data as an observation. So for the purpose of comparison, we prepared 3 models to calculate the posterior predictives. So the first model is a Bayesian neural network whose prior is given by isotropic normal distribution. And the second model is our BNN, whose prior is given by the ridgelet prior. And the last model is a Gaussian process. So the choice of covariance function of this Gaussian process is periodic kernel, which is written as below, like this equation. So the sample pass behavior of this periodic kernel Gaussian process is illustrated as follows. So we can see that this Gaussian process have some periodicity, and the ridgelet prior encode this sample pass property into the Bayesian neural network's parameter space. Okay, so before taking a closer look at each posterior predictives, we would like to mention about our way of posterior sampling. So now we only consider the one hidden layer Bayesian neural network, so which means we have some chance to derive closed form solution of posterior distribution in terms with the last layer parameter distribution. So to utilize this closed form solution, so we basically, actually the exact form of the closed form is actually, we skip the exact form of the posterior distribution, but to utilize this advantage, firstly, we sample the first layer parameter by elliptical slice sampling. Then we sample the last layer parameter from this analytical distribution. And we repeat this process 1 and 2 until we get sort of enough number of parameters. That's how we sample from the posterior distribution. And the reason why we do this, the reason why we employ this procedure is simply, the use of analytical distribution could increase the some accuracy of the posterior predictives. Okay, so now we turn to each posterior predictives. So as we can see here, the Bayesian neural network, whose prior is isotropic normal, fails to capture some periodicity structure behind the data, as we can see here. But on the other hand, the Bayesian neural network with our prior and the Gaussian process successfully captures some the periodic structure behind the data. Okay. So we also use another data set to perform the same experiment. So this data set, airline data set, represent annual change of international airline passengers in the United States. So again, the input is time, and the output is the number of airline passengers. So even if even in this case, we can see that our Bayesian neural network in the Gaussian process both captured some periodic structure behind the data. Okay, so this was the experiment result on prior predictives and posterior predictives. And now we turn to theoretical results on approximation and convergence of this Bayesian neural network. So our theoretical analysis is now limited to the one hidden layer Bayesian neural network case, because as we may know, the analysis of deep version of Bayesian neural network have a lot of challenges and take a lot of time. So it's the deep version of this analysis is definitely our future work, and still have a lot of room to tackle. Okay, so as Chris explained in the former half of this presentation, applying the ridgelet discretization for Gaussian process F leads to one hidden layer Bayesian neural network, which denoted by I sigma DNF. So, so what I mean by ridgelet discretization is, first we expand this original function f by ridgelet transform and discretize this integral by some way. That's what I meant by ridgelet discretization. So at the first glance, this Bayesian neural network I sigma DNF seems to converge to original function f because it just came from the discretization of original integral. So our question is, does this DNA, I sigma d and f, really converge to original Gaussian process? That's our question in this section. And the quick answer to this question is yes. Actually, our analysis suggests that this Bayesian neural network converges to original Gaussian process. So before going to the actual convergence result, we'd like to note that two technical details. So the first one is about related to the first integral here. So basically, we only consider that there's some Gaussian process on compact domain. So so basically we consider this integral on some compact domain. That's kind of one technical details. Then the second technical details is about the second integral with respect to W and B. So to discretize this second integral, we use the random sample Wi and Bi, but the computationally it is impossible to sample from Lebesgue measure. So instead of Lebesgue measure, so in this case, instead of Lebesgue measure, we consider some finite measure, which is denoted by sigma, lambda sigma asterisk. So actually this lambda sigma asterisk can be anything like Gaussian or Laplacian, but as a simple example, this is just an example, this can be anything, but to give you some insight, as a simplest example, we are showing some unit function on some interval. So we can imagine that, okay, so please consider this parameter sigma is a sort of wise of this unit function, or we can say variance of this measure. So in this case, we can imagine that if we take sufficiently large sigma, this finite measure lambda, in some sense, converge to the Lebesgue measure. So, and we use some normalized version of this lambda sigma asterisk as this lambda sigma here.
Takuo?
Okay, that's how we sample. Yep.
Sorry to interrupt, but we have a question from Eric. Could you compare how well your network could perform on the Mauna Loa CO dataset, or some other example, if you don't use the analytic approximation of a final layer? That's the first question. The second question, does that provide useful insight into how well your deep neural networks perform when it's not practical to integrate analytically?
Yes, okay. So for the first question, the first question is about a case we don't use this analytical solution of the posterior distribution. So in this case, yeah, sorry, I think we don't have any pictures, but we can definitely compare two results. First result is our case. First case is the use of the posterior closed form solution of posterior distribution. And the second case is, let's say, another method. Let's say, for example, variational inference or something. In that case, sorry, again, we don't have any picture, but as far as we tried, yes, so if we use the variational inference with very vanilla setting without any tuning, we can see, for example, if the observation looks very complicated, we can easily fail if we use variational inference. But maybe interesting thought would be, in case of variational inference, we use the sort of the isotropic normal distribution as a variational family. So which means that variational family doesn't have any correlation structure between each dimension of parameters. So it's quite, conflict with our concept, because the correlation structure between each dimensional parameter is very important to our in our analysis or to get the desirable result. So so again, the variational inference may fail, but at the same time, it also more or less makes sense to us because they don't have any correlation structure. The second question is, does that provide useful insight into how well your deep neural network perform when it's not practical to you? Okay, so that's the useful insight into how well it perform. Yeah. So could I ask, this second question is about maybe we have some hint or key to extend this method for deep neural network. Maybe that's kind of the meaning of this question.
Yeah.
So.
Oh, sorry, Takuo.
Oh yeah, please go ahead, Chris.
I was just going to say, I think my my interpretation of the question is actually what you just explained. So I think the question is asking, does our method lead to a posterior which is more challenging to approximate computationally compared to a more default prior distribution? And I think your answer suggests that it might do, but that it's kind of inconclusive.
Yes. So you mean that in our case, the posterior distribution becomes more difficult to sample? Then, yeah. But actually, when it comes to the deep neural network, I think it's really always difficult to make some meaningful comments or nice insight or nice suggestion. Because we may not have the nice clue to it becomes difficult to think about the deep version of this extension. But so
we have another question from the same attendee, Eric. Thanks, Chris. Even if it's not more difficult to sample from, in practice, does that sampling cause the good properties of your ridgelet-based PNN to go away?
Yeah, so that's another good question. So, so if I interpret that in a slightly different way, is the poor performance of the standard Bayesian neural network in part driven by the fact that we haven't been able to exploit this conditional Gaussianity to get a nice approximation of the posterior? My feeling is that that's not the case. I think we were able in these simple enough models to accurately approximate the posterior in both cases. But these examples are quite shallow. Many of them are one layer neural networks. So we were actually sort of deliberately avoiding the potential to confound our experimental results with this kind of issue. But it's a really important question because, of course, if we want these things to be useful, they have to be capable of being approximated. And we, like many other people who work in this area, I think are waiting for the leading minds in Monte Carlo, people like Nicola, to come along and tell us how to do this in a very efficient way. Thanks, Eric.
I make no promise. Okay, guys, I think you can proceed.
Okay. So sorry for that. Maybe I misunderstand the meaning of the question, but thanks, Chris, again for helping me with the comment. So I wanna go forward. Okay, so basically we consider our random sample comes from some finite measure, which can be sufficiently close to the vague measure. Okay. So some kind of important variables in our analysis is this, the sort of variance of this finite measure sigma, and the number of the discretization number of first integral d here, and the number of the discretization of second integral n here. That's kind of important variables. Okay, so under these technical details, the BNN with the ridgelet prior actually converge to the target GP in some sense. Okay, so basically this convergence is the convergence between two stochastic processes. One is Gaussian process, and the another one is a Bayesian neural network. So, and to discuss about the convergence, we definitely need some criteria to measure convergence. So this leads us to this slide. So in this paper, we define our criteria of convergence by this formula. So which we call maximum root mean square error. And in this equation, the F is Gaussian process, and the I sigma D and F is a Bayesian network. So we take the square of difference between them. Then we take the expectation with respect to Gaussian process F. And finally, we take Spearman value over some compact space X. Okay, so then one may say, okay, so this is a definition of convergence criteria, but one may ask how reasonable this convergence criteria is. And for this question, we'd like to mention about the Karunen-Lebe theorem. So the statement of the Karunen-Lebe theorem is here. So, okay, so let eta I and the phi I is eigenvalue and the eigenfunction of GP covariance K. So the Karunen-Lebe theorem states that the any Gaussian process sample pass F can be linearly expanded by this linear combination of the eigenfunctions phi I, and whose covariance, whose coefficients mu I is a random variable following some normal distribution. So that's the statement of Karunen-Lebe theorem. So, and as one justification of this convergence criteria here is that even Karunen-Lebe theorem uses this convergence criteria the convergence criteria of the convergence between the original Gaussian process sample pass and this expanded form. Okay. So, and furthermore, it is interesting to compare Karunen-Lebe expansion of Gaussian process and the Bayesian neural network approximation of the Gaussian process, which is our case. So if we apply the ridgelet discretization for Gaussian process sample pass F, we have this expanded form of Gaussian process sample pass. So we can see that basis function, in contrast to KL expansion, that our basis function here is the activation function of neural network. So we'd like to note that the coefficient CI and the other parameters WI and BI are all random variables. So yeah, so in contrast with the KL expansion, the one challenge appearing in the BNN approximation is the even basis function here, phi WX plus B, is random elements. So that is kind of one challenge in BNN approximation case. Okay, so in the next slide, we are going to show you that exact convergence rate between Bayesian neural network and the Gaussian process. But before moving on to it, we just wanted to quickly remind you some setting we are using for this analysis. Okay, so basically, we assume that the first layer parameter follows some prior distribution, PW and PB, which have zero mean, and some variance, sigma W and the sigma B. Yeah, and this first layer prior, PW and PB can be any distribution as long as they have this mean and this variance. So the last layer parameters follows this specific normal distribution, which is defined through the ridgelet prior. And this matrix here, the matrix psi is defined through these equations. So for the scaling constant mu I, we use this value, which depends on the variance of the first layer prior. And this function psi is given by the ridgelet transform. And finally, this evaluation point xj here is given as the grid points on some hypercube, which includes this compact space X. Okay, so this is a setting, but if you are interested in the more specific setting and a more formal definition, please check our archive paper as well. So yes, so under this setting, the exact convergence rate between the Bayesian neural network and the Gaussian process is given as following. So for any Gaussian process which have differentiable mean function and a differentiable covariance function, have this upper bound of this maximum root mean square error. So this upper bound looks a little bit chaotic at the first glance, but basically it can be decomposed into three terms, this first term, second term, and the third term. So the first term is some term related to the variance of the first layer priors. And the second term is some term related to the number of the evaluation points D. Here, the evaluation points appears inside the matrix of psi here. So the D denotes the number of these evaluation points. So the final term is some term related to the number of hidden units of Bayesian neural network. So we can see that if we take the large size of variance, sigma W and sigma B, this first term can go to 0. And the second term, it's same as, second term is also same. If we take the sufficiently large number of D, the second term can go to 0. And finally, if we take sufficiently large number of N, this third term can also go to 0. But of course, this D, N, and the sigma W and the sigma B have to satisfy a certain rate of increase to achieve 0 in all terms. So, but as long as this sigma W and the sigma B, D, and N satisfy some certain rate of increase, we can achieve, we can make all terms to go to 0. So, but also we must acknowledge that there is some curse of dimensionality, especially the term sigma W powered by D, and also large D powered by 1 over small d. Okay, so also this convergence rate is not first at all. But our aim here is to show Bayesian neural network are theoretically capable of converging to any differentiable GP. So it is already known that, as Chris explained in the in the previous slide, it is already known that Bayesian neural network converge to certain Gaussian process in their limit. But our result also shows that Bayesian neural network actually can converge to any GP as long as if we have some more complex prior in theory. Okay, so we can also informally see this theorem as sort of analogy of universal approximation theorem. So the universal approximation theorem states that the non-Bayesian neural network can approximate any continuous function. So we can see that this theorem suggests that the Bayesian neural network can approximate any differentiable GP in some sense. So one may draw some loose analogy between the classical universal approximation theorem and this theorem. Okay, so this is a final section of our presentation. So we finally checked the convergence rate of Bayesian neural network with some experiment. So here we are interested in how first Bayesian neural network converge the Gaussian process in terms with the number of hidden units n. So for that purpose, we fix the all variables except n fixed as this value. So we have 4 variables to change in this upper bound in this convergence rate. So firstly, we fix sigma w equals 5 and sigma b equals 36 and the d equals to 200. Then we change the number of n from smaller value to larger value. And our target Gaussian process is zero mean Gaussian process with some Gaussian covariance. And our activation function is hyperbolic tangent. So we can see that, first of all, we can see that the sample path behavior of this Bayesian network actually get closer and closer to original GP as we increase the n. Okay, and we actually show the exact number of this maximum root mean square error. So this left-hand side picture shows the shows the value of the maximum root mean square error. So the x-axis shows log scale of number of hidden units n, and the y-axis shows the log scale of this maximum root mean square error. So we can see that this slope of this curve roughly follows the 1/2. So this this slope 1/2 is actually compatible with the rate which our theorem suggests.
Takuo,
Okay.
sorry, can I?
Yep.
We have a question from Sho Sonoda.
Mm-hmm.
The M is assumed to be C1 RD, but C1 function are not always L1 RD. Do we need additionally to impose some decay property and infinity on M?
Okay, and thank you for this question. And actually, we skipped some technical details, but so basically we only consider. Sorry, maybe this slide is fine. Okay, so we basically focus on compact domain, and actually there is some technical detail which we skipped. So to consider this compact domain approximation on compact domain, actually we multiply some special function which we call modifier to cut off some domain of function f. So which means we ignore the some domain of f which is outside of this compact space X. So so because of this ignorance, the assumption or of these, the assumption of C1 is no problem in our analysis. And this is some technical detail which we skip in this presentation. So so you can check our archive paper to look into the detail.
Takuo, sorry, do you think you could wrap up in a few more minutes?
Oh, yes,
Because
exactly. Sorry, it's
half an hour behind
maybe.
schedule.
Oh, sorry. Thank you so much for reminding me. Okay, so actually this is the end of our end of the last slide, almost last slide of our presentation. And we also show that, yeah, the covariance function of our Bayesian neural network, and which is the covariance function of our Bayesian neural network also just goes closer and closer to original Gaussian process covariance. Okay, so thank you so much for listening to this very long talk. But to conclude, we defined the ridgelet prior, which enable BNN, enable approximating any Gaussian process. And yeah, and using ridgelet prior, one may easily encode the Gaussian process sample path property into Bayesian neural network sample path space. And we also derive some error bound, which gives us some loose analogy of universal approximation theorem. So yeah, so actually there is still a lot of limitation of the ridgelet prior, but we would say that this research could give us some insight to make some things forward. And yeah, so thank you so much for listening. And this is the end of our presentation.
Thank you very much. Is there any other question from the audience? Let's wait just 20 seconds to see anyone types a question. Well, otherwise, on behalf of everyone, let me thank you again for your talk, and let me clap your talk.
Thank you.
Thanks a lot, Takuo. Thanks a lot, Chris. That was very interesting.
So sorry for running out a lot of time.
That's okay, no problem.
Can I just add my thanks to everyone for coming along and for all the interesting questions that we had. It's some food for thought for us as well.
That's thanks for the question. Very interesting.
Okay. There is one more, isn't there? Oh.
Yes, actually, there's one more question.
Oh, we get the copy of the presentation. The video will be up soon. Oh.
Great, and thank you, Nicola and David, for organising. It's been very enjoyable, and I look forward to joining you for future talks in the series.
Yeah.
So I think the next one is in 2 weeks' time, but don't take my word for it. Check the webinar website.
Yeah, we should have the registration up very shortly. A little bit delayed. Okay, thank you.
Goodbye, everyone.
Thanks, everyone.
Bye.
Thanks so much.